This is a finite element analysis of a motocross bike piston by Daniela Lopez, Andre Barcode, and Ricardo Lara. A piston is a component of an engine whose main purpose is to transform heat energy into rotational motion that can propel the vehicle forward. In this case, the vehicle is a motocross bike. The piston for this simulation is made of aluminum alloy 7075-T6, and its application is within a 4-stroke motocross engine. This type of aluminum alloy has a yield strength of approximately 505 megapascals. In an internal combustion engine, such as the one found in a motocross bike, a thermal gas explosion at a temperature of approximately 300 degrees Celsius causes the gas molecules in the space above the piston to excite and expand. In turn, this sudden expansion creates a force that pushes the piston downward. This force is somewhere in the region of 28,000 newtons, or 6,300 pounds. The piston, which is attached to a connecting rod, transfers this downward force to a crankshaft, which utilizes it to create rotational motion that can propel the bike forward. While this force was applied to multiple iterations of piston heads, the largest stress experienced by the model was always below 200 megapascals. These values are well below the yield strength value of our alloy. This slide depicts the thermal analysis of the bowl-shaped piston head. We applied a temperature of 300 degrees Celsius to the top of the piston head, and as shown in the image, the red region denotes the highest temperature location. For the modal analysis portion of the report, we aim to copy possible vibrational stimulants which a piston may experience in everyday use. One of these stimulants is engine knocking from improper air-to-fuel ratios. This can be caused by numerous factors such as engine life, type of fuel, and ECU mapping. This slide introduces the fatigue analysis that is endured by the piston assembly. The solid lines in the graph depict the fatigue stress amplitude versus number of cycles for the aluminum alloy that we chose. Accordingly, the endurance limit can be estimated to be approximately 159 megapascals or 320 kilonewtons over the course of 10 to the 6 cycles. For the closed-form solution, two analyses were depicted. First, a bending moment would be calculated to provide an understanding as to the performance of a certain shape or material of the connecting rod. Furthermore, the non-binding variable is the cross-section shape or moment of inertia of the connecting rod, and the length of the stroke. Torsion was also analyzed to provide performance results of various polar moments of inertia of the connecting rod's cross-section. We simulated the conditions that an actual piston would undergo in order to verify that our choices in materials, fixtures, and loads were correctly implemented. If a higher load was applied, there would be higher stresses and more deformation. Due to the high force and high temperature conditions of the environment of a piston assembly, the materials and shapes must be meticulously researched and machined to eliminate premature fatigue and failure.